Hello everyone. So I recently made a video about how to integrate sine squared of n pi x over a from 0 to a, where n is an integer, and I did it using a graphical method and a symmetry argument rather than directly performing the integral. But after that, I started thinking about what would happen if instead of sine squared we had sine to some arbitrary positive integer power. So I decided to give that a go, and I found that the result was pretty interesting. So I'm going to share that with you today and show you how to work through it, and also explain my thought process and how I knew to try the method that I tried. So we're going to evaluate this thing, which I've called IM, right? So this is just, we're raising our sine to some arbitrary natural number power. So there's this m here, and then the n inside the brackets is also an integer. So let's make a start on this. So the first thing I did is basically thought, well, as this integral is written, as it is now, right, we don't really know what to do with it. However, if we had a cos term in our integrand along with our power of sine, then we would be able to make some progress, right? Because imagine differentiating a power of sine. You are going to just decrease the power of your sine by 1, but then from the chain rule you're also going to get a cos term, right? And so we could, if we had a cos term in with our power of sine, then we could just use the inverse of the chain rule to figure out what the integral of that thing was. And so how can we get a cos term in our integrand? Well, there's a very nice relationship between sine and cos, right, in that sine squared plus cos squared is 1. So I'm going to use that, and I'm going to keep this as, it's still going to be, of course, the integral from 0 to a, and I'm basically going to take out a factor of sine squared, and then write the factor of sine squared as 1 minus cos squared, okay, just from the well-known trig identity that I just mentioned. So what I'm going to do is write here 1 minus cos squared of n pi over a times x, right? So this bracketed term, this whole thing is equivalent to the sine squared n pi over a times x. But then we still have m minus 2 more sines multiplied together, right? So we've still got sine to the power of m minus 2 of n pi over a times x. Okay, so we've just used a trig identity there, and actually this makes things work out kind of nicely, right? Because we can split this into two integrals, okay, because we've got a 1 and then we've got a minus cos squared. Now if you turn this into two integrals, our first term is just going to be the integral of 0 from 0 to a of just 1 times sine to the power of m minus 2 of all of this stuff. And that looks very much like our original thing that we're trying to evaluate, im, but we've got an m minus 2 instead of an m. And so we can just write that as I subscript m minus 2, right? So that's the first term, which comes from this 1 here. So how about the other term? Well, let's just write that out explicitly. So we've got the integral from 0 to a, so integral from 0 to a of, so we've got a cos squared term, but for reasons that I'm going to explain in a moment, I'm going to write the cos squared explicitly as the product of two causes, all right? So I'm going to say cos of n pi over a times x, but then because it's squared, we have another cos of n pi over a times x, like that, and then this sine is still around, so we get sine to the m minus 2 n pi over a times x with respect to x. Now the reason I've written this, split up this cos squared, relates to what I was saying earlier about using the inverse of the chain rule, because if you look at just this part here, right, so the second cos combined with the sine to the power of m minus 2, that is something that we can actually directly integrate, and because of that we can use integration by parts on this integral that we've come up with here. So in integration by parts, right, we split our integrand into two functions, and we can call this one u, this is kind of the standard notation, and we can call this one dv by dx, okay. So if you're not familiar with integration by parts, you might want to go and read up on that, otherwise this next step might not make a lot of sense. But when we do integration by parts, we're going to get im is im minus 2. Then what we get is our first term is going to be uv, right? So we have to integrate this dv by dx, and so we get a uv term. So we get this u doesn't change, right? So it's going to be the u part is going to be cos of n pi over a times x. And what if this whole bracketed term here is dv by dx? What would v itself be? Well, it's going to be, let's just think about how to invert the chain rule, right? We're going to get a factor of a over n pi. Okay, that comes from the coefficient of x in the argument of the sine. And then we're going to get sine to the power of m minus 1 times... sine to the power of n minus 1 of n pi over a x, and we have to divide that by the power m minus 1. Okay, and this works very nicely because we have this cos here, right? So that's why I introduced the cos in the first place. And so if you're not completely convinced by that, just try directly differentiating this expression here, and you'll see that you get back to this. Okay, so that's something with experience you'll just be able to kind of spot how to integrate using the inverse of the chain rule, right? And then we've got to evaluate this at 0 and a, okay? And then we're going to get another integral term, okay? And the other integral term is going to be the integral of v times du by dx. And we have to subtract it off, but because there's already a minus sign here, I'm going to put a plus in front of this integral. It's still from 0 to a. And so remember, it's going to be v du by dx. So what would du by dx be? Well, we're just differentiating this cos term, and so cos differentiates to minus sign, and we get this extra factor of n pi over a in the front from the chain rule. So n pi over a minus n pi over a sine of n pi over a times x, right? And then we've got to multiply by v, which is this thing that we calculated before, and so we can just write that there. So it's going to be a over n pi times sine to the m minus 1 of n pi over a times x, all over m minus 1. Okay, and that is with respect to x. Alright, so this simplifies in a very nice way. It's less kind of intimidating than it actually looks, because what's going to happen is we get im is im minus 2. And what's going to happen, let's think about this bracketed term here, this term in the square brackets. So if we put in x equals a, right, if we put in x equals a, so when we use this top value in the square brackets, this sine term here is going to be just sine of n pi, right? And sine of n pi is always 0, and so that's just 0. And what happens when we put in x equals 0? We again get sine of 0, and so this whole bracketed term just disappears, turns into 0. So we don't have to worry about that, which is nice. And then how about this integral here? Well, there are a few things we can notice, right? So firstly, this n pi over a cancels with this a over n pi. And then we can combine our powers of sine together, and we just get back sine to the mth power, right? Sine to the m of n pi x over a divided by m minus 1. But that's exactly what we started with, all right? And so also note there's a minus sign here, so I can say minus, and there's an m minus 1 here, so I'm going to say minus 1 over m minus 1, and then because we have sine to the power of m, it's exactly what we started with, and so we can just write our integral that we left with as just im. Okay, so what can we do with this? We can just rearrange it a bit to make it a bit, well, just put it in a nicer form, right? So if I collect the ims onto the same side, we get 1 plus 1 over m minus 1 times im is im minus 2, and then just rearrange this a bit, do some algebra with this fraction here. You will find that im is equal to m minus 1 over m times im minus 2. So we've derived this nice relationship between im and im minus 2. And this is what's called a reduction formula. Okay, we relate the integral with the sine to the power of m. We relate that directly to a similar integral but with a power of m minus 2, right? This is called a reduction formula. And what you can see, right, we relate, because you've got an m here and an m minus 2 here. Let's say we start with I2, right? Well, from I2 we can calculate I4, and then from I4 we can calculate I6, and so on. And so if we know I2, we can calculate all of the even powers, but we can't calculate the odd powers because you're kind of changing your m by 2 each time when you use this reduction formula. So what that means is that we're going to get different results for even and odd values of m. Okay, so what I want to do is just consider the even and odd values of m separately. So let's think about the even values first. Now, actually, I'm just going to write here, we already know that I2 is equal to a over 2. So this was the subject of my previous video. Okay, so we evaluated this integral using a neat symmetry argument, and found that the integral of sine squared over this range is just half a. All right, so given that, you might want to have a quick look at that video just to convince yourself how that works. But given that I2 is just a half of a, we can figure out I4. Alright, so I4, if we just plug in m equals 4, we're going to get 3 quarters, right? M minus 1 over m is going to be 3 quarters. So let me just write out here, I4 is 3 quarters of a over 2, right? And from that, we can get I6, so we just plug in m equals 6, right? And so, what are we going to get? 5/6 times I4, but I4 itself is 3 quarters of a over 2. And we can just keep going, right? If we wanted to get I8, it would follow the same pattern. We get 7/8 of 5/6 of 3 quarters of a over 2. Alright, so you start to get this nice pattern emerging where you've got all of these odd numbers multiplied together on the top and all of the even numbers multiplied together on the bottom. Alright, and another thing to notice about this is because I2 doesn't depend on n, right? So n, remember, this was the integer which is inside the integrand, inside the argument of the sine function. None of these have any dependence on the integer n. All right, so this is also related to the symmetry of the functions, right? So that is the results. These are the results for even values of m. So what happens if m is odd? So let's make a note about that here. So if m is odd, what can we do? Well, we need to start, if we want to use our reduction formula, we need to start with a known integral that has an odd value of m, and the easiest one to evaluate, of course, is just when m equals 1, right? So let's figure out I1. So I1 is just the integral from 0 to a of sine to the power of 1, which is just sine of n pi over a times x with respect to x, right? This is a very simple integral to do. It is going to be a over n pi, right? Just integrating sine, it becomes minus cos, right? So a over n pi cos of n pi over a x. And because sine integrates to minus cos, I'm going to flip around the limits. I'm going to put an a here and a 0 here. So the minus sign has been kind of absorbed into the limits. And this is a over n pi times 1. Right, if we plug in x equals 0, we just get cos of 0, which is 1. Then 1 minus, when x is a, we just get cos of n pi. All right. So how can we simplify that? Actually, we can split this into two cases, right? So think about if n is even, okay, if n is even, cos of n pi is going to be, so if n is even, cos of n pi is just going to be 1, right? So we can write that as, well, it's just going to be a over n pi times 1 minus 1, right? Because if n is even, we get cos of 0 and then cos of 2 pi and cos of 4 pi and so on. And so all of those cosines are 1, so we just get 1 minus 1 in the brackets. And so it is 0 as long as n is even. So how about if n is odd? Then it's going to be, cos of n pi is going to be minus 1, right? Because we're going to have cos of pi and then cos of 3 pi, cos of 5 pi, and so on. Those are all minus 1. In that case, we get 1 minus minus 1, which is 2. And so this is 2a over n pi when n is odd. All right, so we've evaluated I1 and found that we can split this into two cases depending on whether n is even or odd. So note that this is different from the case where m is even, right? When m was even, we found our results up here didn't have any dependence on n, whereas here I1 does depend on n. It depends on whether n is even or odd, and in the odd case, actually the value of n turns up in the value of our actual integral. Okay. Basically, this is because if you have an even power, your function is squared, right? And so it's always positive. If you have an odd power, so when m is odd, the function spends some time above the x-axis and some time below the x-axis. And so if you can convince yourself of this by drawing a little sketch, actually. If n is even, then like the function spends, the sine term spends as much time above the x-axis as below the x-axis, and so everything cancels. The areas, positive areas cancel with the negative areas, and you get 0. Whereas if n is odd, you end up with a bit of area left over that is not cancelled out. All right. So that's why there's this difference between the odd and even values of m. Okay, so now we can use our reduction formula. All right. So remember, we want to be using this formula up here. So let's again, because I1 depended on n, we're going to split our general I1, I3, I5, and so on into two cases, depending on whether n is even or odd, right? So if n is even, what's going to happen? Well, I1 is 0, which means I3 is also 0, right? Just from here, from this formula up here. If I3 is 0, then I5 is also 0, and so you can just keep going, right? I to an arbitrary, I subscript some arbitrary odd number, which you can write as, let's say, 2k minus 1, where k is a positive integer. All of those are going to be 0, all right? Because all of these integrands spend as much time above the x-axis as below the x-axis. So how about when n is odd? Okay, we know that I1 is 2a over n pi. That's what we calculated. So let's use that to figure out I3. So I3, again, going back to here, we're going to get 2, m minus 1 is 2, m is 3, 2/3 of 2a over n pi. then let's keep going. I5, all right, I5 is going to be 4/5 of the stuff we just calculated. 4/5 of 2/3 of 2a over n pi. And let's do one more. I7 is going to be 6/7 of 4/5 of 2/3 of 2a over n pi. All right, so it looks kind of similar to what we had for the previous case when m was even. A couple of differences. We've got this n here. Which is about the symmetry of the function of the integrand that I mentioned before, and we also have like the even and odd numbers have kind of flipped around, right? So now we've got all the even numbers multiplied together on the top and all the odd numbers multiplied together on the bottom. Okay, so there you go. I thought that was kind of an interesting result. We end up with these very nice expressions for all of these IM values. I hope you enjoyed that, and see you again soon to do some more maths and physics.